So, this is lecture 11, part 1, integration technique. Integration is, I guess, is a little bit more difficult compared to differentiation. So, you need to use some of those techniques to evaluate the integration. Differentiation pretty much straightforward compared to integration. Okay, start from coffee break. Wow, even before you do we do the lecture, we go into the coffee break. Isn't that nice? I love coffee. Okay, integration of 1 over x. Okay, as I said before, last lecture was it? There is an interesting case of integration of this one here. So let's take a look at the differentiation of cube power, second power, first power, zeroth power, negative 1, negative 2, negative 3 powers. Differentiated, you get 3 times x squared, blah, blah, blah. This is 1, this is 0, this is minus 2, minus 3, minus 4. Okay, no problem. But if you integrate those, well, this one goes back to x cubed, this one goes back to x squared, this one goes back to x to the first power, and this one here. Since this is equal to 0, integral of 0 is, of course, 0. And minus 2 power, minus 1, minus 2, minus 3. So, all except this one, you can recover by integrating. Meaning that here, this is a place where symmetry is broken. Okay? What's going on there? Where is x to the 0th power? How do we approach this one here? In other words, integrating that we cannot come back to x to the 0th power. More coffee. Integration of 1 over x. So, how should we approach? Well, we do this all the time, don't we? Approach from the back door. Since we are engineers, we can do this. We know the answer. Okay, this one here. And whenever you have log function, okay, try exponential, because exponential is something which is reverse of that one, so we'll give you hints and so forth. So, since this is ln x, let's set x is equal to e to the yth power. Then what's going to happen is that if you differentiate x in terms of y, you're not differentiating y in terms of x, okay? Okay, so be careful, okay? You are differentiating x in terms of y. Then e to the y differentiating in terms of y, so that's e to the y, because it doesn't change, right? And e to the y is what? That's x. So this is what you got. And from this one here, you can divide both sides by x, and you get this relationship. You know why I'm getting this relationship, right? Because you want to integrate 1 over x. Aha! So, the next thing is we integrate this with respect to y. WRT stands for with respect to y. So, integrating in terms of y, and the other side is just 1. So, 1 integrating the y, that's y plus c. Don't forget c. And for this one here, you can use rule c, right? So, applying rule c, this one becomes 1 over x dx. And which is equal to y plus c, and y was what? But from this relationship, y is log x. Wow. So, you get this one here is equal to that one there. QED. That's the end of the proof. Okay? So, whenever you have something which is difficult to solve, go around that. Okay? Engineers are allowed to do that. Okay? Okay. So now serious stuffs. Examples. 1 and 2. Rules A, C, and D, I use that. Here, if you have, we have 5e to the sine theta power times cosine theta. And the sine thetas and cosine thetas, as you can immediately tell that if you differentiate sine theta, you got cosine theta. So let phi be sine theta, then differentiating that in terms of x, no. Of course, you are differentiating in terms of theta, right? Then cosine theta. So this integral here is dx theta. And rule C says this is nothing but that. And since this is exponential, that's e to the phi plus C. Not quite, right? Actually, 5 is sitting outside, so this is like this one here. Okay? But since C is integration constant, which we don't know yet, so 5 times C is, once again, just a constant. That's why it is perfectly okay to write this one here plus C. And if you don't like it, well, you can call that C1 or something other than that, C1. All right, so that's easy. So the catch was this one here, right? C. Yeah, rule C. The next one here is x times e to 3x. This type of function here, this is a product. So therefore, you need to think about two things. One of them is like this one here, rule C. The other one is rule B, the integral of the product. Here, this is example of the integration of the product. As I said, you choose f in such that in such a way that df dx is easy. So here, what I did was that I chose fx to be x. Then the derivative of that is equal to 1. At the same time, it is equally important to choose g dg dx to be something for that g is easy to find. Okay, here I put this to be 9 times e to 3x. And exponential functions are very easy to integrate because it does not change. And if you look at this one here, 3x, so 1/3 comes in, so that's 3 times e to the 3x. Okay? So, exponential is a very good function to choose for this one here. Well, of course, sine, cosines, you know what those are. And x is some power, you can do the same thing. But anyway, so this one here is x times this is g. The minus this is df dx times this one here. And 1 times 3 times this is nothing but e to 3x dx. Now the integral is just 1/3 of that, so 3 goes away, and this is that. Any questions? Well, too bad that this is not a real lecture, so I cannot answer your questions. So please send the questions to your teacher. Okay. Simple and easy. Well, let's move on to the other one. Rules A, B, and D one more time, except that now you have e to the 3x times cosine 2x. E to the 3x, differentiated or integrated, you get e to the 3x again. But cosine, differentiated sine, integrated sine, both you get sine. Does not get simpler. But one thing we know is that if you differentiate this twice, you go back to the original one. You integrate this one as many times as you like, you get exactly the same e to the 3x. Okay? So we use that fact. Okay, first step, it doesn't matter, but let's put this one here to be cosine, then this is minus sine. Once again, dg dx e to the 3x, because gx can easily be found, 1/3 of this one here. Okay. So this one here is 13 times this, that, minus this, that. So it looks like this one here. Probably you are wondering why this 13. Well, we instructors, teachers, tends to choose those numbers which can be used for canceling certain numbers. And you will see that 13 is a very cozy, easy number, very convenient number. Well, let's see that. Okay, here, this integral is this plus that, and you still have this. Instead of cosine, we have sine. Oh, okay. So if in the second step, if we do pretty much the same thing, fx equals sine 2x, then you get cosine 2x. Go back to the original one. Okay. And the exponential doesn't change at all. So if you do that, you got this one here, the sines, and this one here. And then inside cosine and exponential. So that's this. We have seen this somewhere here. So this portion here, and of course 13 is altogether. That's I. So original integral comes back again. So what's the next thing you have to do? That's I. So you move that to the other side. You get, that's 1 plus 4 over 9. That's 13 over 9. 13. Magic number. That's 13 times this plus that. So you get rid of 13 over 9, both sides. You get this one here. Great, you're done. Right? Wrong. Is this correct? Some of you have already noticed that where is the integration constant c? Okay, as I said before, when you do have indefinite integral, that's fine because you haven't evaluated that. But once you move to the other side and then you don't have indefinite integral on this side. So therefore, what's going to happen is that you have to have c. How? You just add c. That's all you have to do. You just add c to get the complete answer. All right. So the catch here was that if you differentiate twice, then you get the original sines and cosines. So whenever you have trig functions, sines and cosines, then you can always use this trick. Okay? Any questions? No? Okay. Don't forget C. Okay, that's fine. Okay, techniques. Some of those techniques can be stated in general way. So let me try to do that for two very famous techniques. First one is involves in trigonometric functions of this form or that form. Well, you have function of cosines and sine x is multiplied to it, or you have functions of sines and multiplied by cosine x. In those cases, the first case you set y is equal to sine x, and second case you set z is equal to cosine x. Then the derivatives are sine x and cosine x. So that one becomes this cosine x. If that is equal to y, then this one here is dy dx. So you can use rule C. To simplify the integral. Example, sine fifth power dx. Is this of this form? At least you have sine. So what I'm going to do is to take one sine x out. Then you have sine to the fourth power left. And now, to make this function, you need to convert into cosine x. But you know that sine squared x is 1 minus cosine squared x. So this is fourth power, so that's 1 minus cosine squared x squared. And computing that one more time, you got this one here. Okay. So, what do you use? Linearity, yes. Rule A. So you can integrate this one separately, three of them, by setting z is equal to cosine x. Z is equal to cosine x. Z is equal to cosine x. Wait a minute. Well, whichever you like. So this is 1 minus z is, and for it. And from here there is, I thought sorry, I didn't write down. So, from here to there is rule C. Okay, so that's this plus C, and put z as cosine x back into it, and you get this one here. Right? Well, actually, whichever the one you find. Well, I guess I made a mistake here. This is not y, this is z, and this is z. So actually, this is z here. And this is y, and this is y. Right? Cosine x is z. Aha! So, on your note, please make this correction here. Okay. Second one is trigonometric functions double angle formula. Well, there are many of those formulas for trigonometric trig functions, so therefore we can use them as tools for evaluating integrals, like sine to the fourth power. If you take one of the sine out, you have sine cube, so you cannot do the same thing again. But the other thing we do know is that the sine square could be written in this form, 1 minus cosine 2x divided by 2. So this entire thing, sine to the fourth power, is a square of that. And by computing this one out, 1/4 of this one here. Now you still have cosine squared here, but you can use, once again, the half angle or double angle formula, whichever you like. And you got this one here. And once you got this one here, the rest is easy, right? Oh, so, how shall I say? When you have sines and cosines in your integrand, those are two techniques you should try. Some of them will work. Caution, no technique is always effective. Or if I said it the other way around, there are different ways of solving or evaluating this integral. And this is not the only method. There are many of them. So try that. And probably that's another reason why students normally don't like integrations. Coffee break, a twist of fundamental theorem of calculus. This is what I like. Okay, how about gx is equal to 0 to 2x fu du, not x, okay? Find this one here, derivative. Ooh, all right, how do you do it? If I let dfx dx to be small fx, then fundamental theorem of calculus says that you integrate this one from 0 to x, this one here is fx minus f0, because you are integrating from 0 to x. So therefore, if you integrate from 0 to 2x, you get f of 2x minus f of 0, naturally. Okay? So, dgx dx here is this one here, because that is exactly g of x, right? So dgx dx is equal to this one in terms of dx. And of course, f0 is just a number, so it is gone. So you're differentiating this in terms of dx. Aha, chain rule, right? dy dy, and y is equal to 2x. So therefore, this one is just 2. So this here differentiated u of fx. So therefore, that's twice as much of f of y, that's f of 2x. Interesting, don't you think? Now, if you stop here, you're not really a good engineer. Well, tools, if you have more tools, of course, you can solve more questions, right? So you always ask, can we generalize this? Or can we make this tool more useful? The answer for this question is yes. The answer for that is more copy, once again, one of many Leibniz rule. Leibniz rule. Leibniz is another one who, Leibniz and the Newton. Those are two giants who came up with fundamental theorem of calculus. And Leibniz invented many rules. This is one of the many, one of very well-known one. Let Ix is equal to, wow, look at this one here. Lower limit has x in it, upper limit has x in it, and integrand has x in it. So it's something else. And you want to differentiate this in terms of x. What's going to happen? You integrate, not integrate, differentiate this in terms of x. You get differentiation of this upper limit times integrand evaluated at upper limit minus differentiation of lower limit here and this one here evaluated at the lower limit and plus differentiation of integrand itself. But since you are differentiating in terms of x and this one has two variables, so differentiation has to be partial differentiation. So naturally, there are three places where x comes in. So you will have three components because you have to differentiate this, and that. So this is a beautiful formula which you can apply to many different occasions. And of course, this is something we have done. Okay. And if you apply this one here, then you get the answer right away. All right? Because this is gone, this is gone. The only thing remaining is this one here. And that's 2, that's f of 2x. Easy. All right? That is the end of this lecture here. And I hope you enjoyed the last one, Leibniz rule. Thank you.